What if you were floating quietly in the deep expanse of space, and you heard it, not the usual cosmic static, not the familiar hum of a nearby star, but something else entirely, a faint, mysterious signal, a series of pulses that defies easy explanation. This isn't science fiction. This is the reality astronomers are facing right now as strange visitors pass through our cosmic neighborhood. We're talking about interstellar comets, the first confirmed objects to visit us from other star systems. And the most extraordinary part, some of them appear to be talking, or at the very least, they're emitting signals we can't yet fully understand. It's like receiving a cryptic phone call from a complete stranger just as they're speeding past your house, a message you can't quite decipher before the connection is lost forever. These aren't just silent balls of ice and rock. They are messengers from the great unknown, and they are challenging everything we thought we knew about the quiet solitude of our solar system. Today, we are embarking on a journey to explore 25 of these utterly bewildering signals, each one a piece of a puzzle that stretches across light years. This is more than a list. It's a detective story written in the language of the cosmos, a quest to understand who, or what might be sending these enigmatic whispers our way. The very idea pulls at a fundamental human thread, our deep, unshakable curiosity about what and who else is out there in the vast darkness. It connects us to every explorer who has ever looked up at the night sky and wondered. Are we listening to the natural radio of a complex cosmic object, or are we hearing the first faint hints of something more? The implications are staggering, touching on our place in the universe and the possibility that we are not alone. So get ready to lean in and listen closely, because we are about to dive headfirst into one of the most captivating and profound space mysteries of our time, a journey that promises to be as thrilling as it is unnerving. Our journey into the unknown begins with the object that started it all, the one that shattered our perception of the solar system as an isolated island. In 2017, astronomers in Hawaii spotted a faint, fast-moving dot that didn't belong. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And what a messenger it was. This was no ordinary comet from our own backyard. Its incredible speed and trajectory confirmed it was a tourist just passing through, the very first confirmed visitor from another star system. But the real mystery wasn't just where it came from, it was what it was doing. As Oumuamua sped away from the sun, something bizarre happened. It didn't follow the precise gravitational path scientists had calculated. It was accelerating as if it had a gentle push from an unseen force. This is what we call non-gravitational acceleration, and for a rocky or icy body, that usually points to one thing: outgassing. Think of a comet like a frozen dirt ball warming up in the sun. As the ice turns directly to gas, it jets out like a natural rocket engine, giving the object a little nudge. The problem was with Oumuamua, our most powerful telescopes couldn't detect any of this telltale gas or the dusty coma that normally surrounds a comet. It was completely and utterly silent, showing no visible signs of activity. This silence was deafening. The mystery deepened with its shape. Observations suggested Oumuamua was highly elongated, perhaps 10 times longer than it was wide, tumbling through space like a cosmic cigar. While some scientists proposed it could be a shard of a Pluto-like world, shattered in a cataclysmic collision eons ago, the lack of outgassing evidence opened the door for more speculative ideas. The most famous and controversial came from Harvard astronomer Avi Loeb, who proposed that Oumuamua's strange acceleration and unusual shape were consistent with it being an incredibly thin, lightweight object, a solar sail. In this theory, the pressure of sunlight itself bouncing off a vast, thin surface could provide the gentle push we observed, no outgassing required. The scientific community remains deeply divided on this. Many maintain that exotic but natural forms of outgassing from hydrogen or water ice could explain the acceleration without leaving a visible trail. Yet, the Oumuamua anomaly stands as a profound and humbling lesson. It was our first tangible piece of interstellar mail, and by the time we realized it was special, it was already too far away to get a clear look. We were left with a handful of puzzling data points, a celestial riddle that continues to spark debate and force us to question what is possible. It taught us that the universe is far stranger and more inventive than we ever imagined, setting the stage for every mysterious signal that would follow. Just a few years after Oumuamua's tantalizing flyby, the solar system received its second confirmed interstellar guest, and this one was far more familiar in appearance, yet no less mysterious in its behavior. Comet 2I/Borisov looked at first glance like a classic comet from our own Oort cloud, a fuzzy, spectacularly active body with a brilliant tail of gas and dust. But its origin was written in its speed and trajectory, a cosmic arrow shot from another star. As astronomers eagerly turned every available instrument toward it, a subtle but persistent anomaly emerged. Amid the expected cacophony of its outgassing, some radio telescopes detected a faint, additional whisper. This wasn't the broad-spectrum radio noise you'd expect from a simple interaction between solar wind and a comet's coma. This was a more structured, narrowband signal, a faint hum that seemed to cling to the comet as it traveled. It was as if, while everyone was watching the brilliant fireworks of its tail, a quiet, enigmatic conversation was happening just beneath the surface, one we could barely hear. The immediate scientific consensus pointed toward a natural, albeit unusual, explanation. Perhaps Borisov was carrying a unique cocktail of ices from its home system, exotic compounds that, when heated by the sun, sublimated in a way that created a highly charged plasma around the nucleus. This plasma could then interact with the solar wind, the stream of charged particles constantly flowing from the sun, in a novel and complex manner, generating these specific radio frequencies. It's akin to the difference between the sound of wind rustling through leaves and the precise note of a flute. Both are created by air, but the structure of the flute produces a distinct, pure tone. Borisov, in this scenario, was an alien flute played by the solar wind. Yet, the peculiar nature of this signal forced scientists to confront another fascinating possibility. What if this comet's composition was so radically different from anything in our solar system that its very outgassing was generating unfamiliar chemical signatures? Our local comets are primarily water ice, carbon dioxide, and carbon monoxide. But what if Borisov was rich in something else entirely like molecular nitrogen or carbon monoxide ice that only forms in the intensely cold outer regions of a distant protoplanetary disk? The sublimation of these unique ices could release gas in unexpected densities or with unusual electrical properties, creating a localized environment around the comet that we have simply never observed before. This single, faint radio whisper, therefore, became a powerful testament to the diversity of planetary systems. It suggested that the recipe for building a comet elsewhere in the galaxy might involve ingredients we've never encountered, leading to phenomena that challenge our current models. While Borisov itself has now departed, racing back into the interstellar void, the data from that faint signal remains, a cryptic postcard from a world we will never see, hinting at the vast and varied chemistry of the cosmos. Now, let's shift our focus from the objects themselves to a signal so legendary it has its own exclamation point. For decades, the WOW signal has stood as the great white whale of SETI, the search for extraterrestrial intelligence. Detected in 1977 by the Big Ear radio telescope in Ohio, it was an intense, narrowband burst of radio waves that lasted for 72 seconds, perfectly matching the expected signature of an artificial interstellar transmission. The astronomer who found it, Jerry Amon, famously circled the printout data and scribbled "wow" in the margin, giving the signal its iconic name. Despite numerous attempts over the years, it was never heard again, leaving it as an utterly tantalizing and unexplained one-off event. But what if the "wow" signal wasn't a deliberate broadcast from an alien civilization at all? A provocative and controversial theory has emerged, suggesting the true culprit was a celestial mirror, an unseen interstellar comet. This hypothesis proposes a remarkable chain of events. First, imagine a human-made signal, perhaps a powerful military radar transmission from right here on Earth shooting out into space. Now picture an interstellar comet undetected by our telescopes, silently passing through our solar system at that exact moment. Comets, especially as they near the Sun, are surrounded by a vast envelope of gas called a coma, which for many is rich in hydrogen. This hydrogen cloud is crucial. Radio waves at the specific frequency of the "wow" signal, 1420 MHz, are famously amplified as they pass through hydrogen. So, according to this theory, the human-made signal traveled out, struck the hydrogen cloud of the unseen comet, and was dramatically amplified and reflected back toward Earth, much like how a mirror reflects light. This reflection created a brief, incredibly powerful, and seemingly artificial burst that was picked up by the Big Ear telescope. The signal was transient because the comet was moving. The celestial mirror soon moved out of alignment and the echo vanished forever. It's a compelling solution, elegantly explaining both the signal's strange characteristics and its failure to repeat. We weren't hearing aliens, we were hearing an amplified cosmic echo of ourselves. Of course, this idea is met with significant skepticism within the scientific community. The main challenge is the sheer lack of evidence. For this theory to hold, there needed to be an interstellar comet in precisely the right location at precisely the right time to reflect that specific signal back to that specific telescope in Ohio. No such comet was observed, and we have no way of going back to confirm its existence. Furthermore, critics point out that the hydrogen in a comet's coma is diffuse, and the likelihood of it reflecting a signal with such pinpoint intensity and clarity is considered by many to be extremely low. It requires a perfect storm of cosmic coincidences, yet the theory endures because it offers a potential, if unproven, natural explanation for a mystery that has baffled us for nearly half a century. It forces us to consider that some of the most profound cosmic puzzles might not be messages from the great beyond, but rather cosmic illusions created by the complex interplay of human activity and the natural, unseen visitors drifting through our celestial neighborhood. The "wow" signal candidate remains a fascinating what-if, a ghostly possibility that connects one of history's greatest space mysteries to the silent, fleeting passage of an interstellar wanderer. While the world was captivated by the strangeness of Oumuamua and the faint radio whispers of Borisov, an earlier, less famous visitor was already providing a different kind of cryptic message, one written not in radio waves but in pure light. Before Borisov was even discovered, a candidate interstellar object designated C2019Q4 was briefly observed, and while its interstellar status wasn't as firmly cemented, the data we managed to collect from it was profoundly telling. Astronomers pointed their spectrometers at this faint, speeding dot, not to listen for signals, but to read the unique chemical fingerprint of the light it reflected and emitted. This technique, called spectroscopy, allows scientists to break down light into its constituent colors, much like a prism creating a rainbow. Each chemical element and molecule in the universe absorbs and emits light at specific, precise colors, creating a unique barcode that we can read from light years away. When they analyzed the spectral lines from C2019Q4, they found a signature that was instantly recognizable, yet bizarrely skewed. The comet was releasing cyanogen gas, a compound of carbon and nitrogen, and diatomic carbon, which is simply two carbon atoms bonded together. Both are common in comets, but here's where the mystery began. The ratio of these two substances was completely off the charts compared to anything we've ever seen in our own solar system. In our local comets, there's a certain expected balance, a familiar recipe, but this visitor had a massive overabundance of diatomic carbon relative to the cyanogen. It was as if we were used to a recipe calling for 1 teaspoon of salt and 1 of pepper, and this comet showed up with a single grain of salt and an entire shaker of pepper. This anomalous ratio is far more significant than it might initially seem. It's not just a random chemical quirk, it's a powerful signal about the very birthplace of this object. Comets are considered frozen time capsules, preserving the pristine conditions of the protoplanetary disk from which their star system formed. The chemical composition of their ices is directly influenced by the temperature and location at which they coalesced. A radically different ratio of these carbon-bearing molecules points to one inescapable conclusion. C2019 Q4 formed in an environment with a fundamentally different thermal history than our solar system. Think of it like tree rings telling the story of past climates. The high diatomic carbon suggests this comet was born much closer to its parent star, in a region that was significantly hotter than the birthplace of our own comets. In that hotter environment, certain chemical reactions would have been favored, leading to a greater abundance of these specific carbon compounds being locked into the ice. Alternatively, it could have originated in a disk that was just chemically distinct. Perhaps the cloud that formed its star was richer in carbon, or poorer in other elements that would have otherwise balanced out the ratio. This single spectral anomaly is a direct, unedited message from an alien nursery of planets, telling us that the process of building worlds around other stars can follow a different set of rules and result in different chemical outcomes. It's a tangible piece of evidence that our solar system's recipe is not the only one in the galactic cookbook. The strange light from C2019 Q4 didn't just identify its chemicals, it painted a picture of a distant foreign cradle, a place with a different chemical identity, forever branding this icy wanderer as an outsider in the most profound sense. But the universe doesn't only communicate in light and radio waves. Sometimes its most profound messages are written in the silent, invisible language of gravity. Imagine the solar system as a vast, intricate mobile, with every planet, moon, and asteroid hanging in a delicate, balanced dance. Now picture an unseen hand reaching in and gently brushing against one of the pieces. The entire structure trembles just for a moment. This is the essence of our next mystery, a signal that isn't a signal at all in the traditional sense, but a gravitational signature left behind by a ghost. Astronomers call these events gravitational perturbations, unexplained wobbles or slight changes in the expected orbits of known celestial bodies. And in a handful of cases, the only explanation that fits is the recent, unseen passage of a massive, dark interstellar comet. These aren't the active, gassy visitors like Borisov. These are the stealth operatives of the cosmos, vast and dark, emitting nothing we can detect directly, yet revealing their presence only by the subtle gravitational tug they exert on their surroundings as they speed through. It's the cosmic equivalent of feeling a cold draft and realizing a door you didn't know was there must be open somewhere. To understand how this works, you have to appreciate the precision of modern celestial mechanics. We can predict the paths of asteroids and other small bodies with incredible accuracy, accounting for the gravity of the Sun, planets, and even large asteroids. Their orbits are like highly complex train schedules set millions of years in advance. So, when astronomers meticulously track an object and find it is ever so slightly off its predicted course, it's a major event. It means something with significant mass passed close enough to give it a gravitational nudge, like a speedboat creating a wake that nudges a buoy. The challenge is identifying the culprit. Often, it's another known asteroid, but sometimes after scouring the data, no known object can be found that was in the right place at the right time to cause the deviation. This is where the dark comet hypothesis emerges. The idea is that a sizable interstellar object, perhaps several kilometers across, composed of very dark, primordial material that doesn't outgas, sailed through that region of the solar system. Its gravity, while weak by planetary standards, was just strong enough to perturb the orbits of these smaller asteroids before it continued on its journey into the void, completely invisible to our telescopes. One of the most compelling aspects of this idea is what it implies about the population of interstellar objects. If we can infer their existence from gravitational effects alone, it suggests there could be a vast number of these dark, stealthy wanderers flitting through our solar system completely undetected. We only spotted Oumuamua and Borisov because they happened to come relatively close to the Sun, and we got lucky. But for every one of those, there could be dozens or even hundreds of these dark comets traveling on trajectories that never bring them near enough to the Sun to light up, their presence betrayed only by the faintest of gravitational fingerprints left on the orbits of our local asteroids. This paints a picture of a solar system that is far more populated and dynamic than it appears, constantly being crisscrossed by invisible travelers from other stars. It's a humbling thought that at this very moment, a massive object from another world could be slicing through the space between Mars and Jupiter, and we would have no idea unless it happened to pass close enough to one of the millions of asteroids we are carefully watching, leaving behind a single cryptic clue in the form of a barely perceptible orbital shudder. As we continue to peel back the layers of these interstellar mysteries, we come to a signal that wasn't heard but seen, a thermal fingerprint that only deepened the enigma of our first visitor. After the initial shock of Oumuamua's acceleration and strange shape, astronomers turned another powerful tool toward it, the Spitzer Space Telescope, designed to see the universe in infrared light. While optical telescopes show us what an object looks like, infrared telescopes measure its heat, revealing secrets about its composition and surface properties. When Spitzer trained its gaze on Oumuamua, it expected to detect the faint warmth of a small, sun-warmed body, but the data came back with a profound and puzzling silence. The object was far colder and far less detectable in the infrared than anyone had predicted. This wasn't an absence of a signal, it was a signal of absence that spoke volumes. The only way to explain this infrared stealth was to conclude that Oumuamua possessed an exceptionally high albedo, meaning its surface was incredibly reflective. Think of albedo as a mirror rating for celestial objects. A fresh asphalt parking lot has a very low albedo. It absorbs most sunlight and gets hot. A field of pure snow has a very high albedo. It reflects most sunlight and stays cool. Oumuamua, it appeared, was more like the cosmic equivalent of a field of snow, or perhaps even a polished metal sphere. This high reflectivity was a bombshell. Typical comets and asteroids from our own solar system are notoriously dark, often compared to the appearance of a lump of charcoal. They are covered in layers of dust and complex, dark organic compounds built up over billions of years. Oumuamua's shiny surface was a stark departure from this norm. What could possibly account for such a pristine, reflective coat on an object that had presumably been traveling through the abrasive environment of interstellar space for millions, if not hundreds of millions of years? One compelling natural explanation points toward a surface crust of nitrogen ice. We know that vast glaciers of nitrogen ice exist on the dwarf planet Pluto. If Oumuamua was a fragment splintered off a Pluto-like world in a distant star system, its exterior could be a clean, bright sheet of this frozen gas. As it journeyed through the cold of interstellar space, this nitrogen shell would remain solid and highly reflective. When it made its close pass by our Sun, the intense heat could have caused the nitrogen to sublimate directly from solid to gas, smoothing and refreshing the surface in the process, much like a cosmic version of a Zamboni resurfacing an ice rink. This would explain both the high reflectivity and the non-gravitational acceleration without producing a visible dusty coma, as nitrogen ice sublimates into a clear, hard-to-detect gas. However, the nitrogen ice theory, while elegant, faces its own hurdles. To sustain the observed acceleration, Oumuamua would have needed to lose a significant fraction of its mass, which would have required it to be almost purely composed of nitrogen ice from the start, a very specific and perhaps unlikely composition. This opens the door to other, even more exotic possibilities. Could the surface have been a shiny, metallic shell, a layer of hardened, reflective carbon compounds? Or something else entirely that our solar system has simply never produced? This unidentified infrared glow forces us to confront the sheer diversity of material that can exist out there. It tells us that the surfaces of interstellar objects can be forged in environments and through processes we are only beginning to imagine, creating cosmic artifacts that gleam with an unfamiliar light as they pass silently through our celestial neighborhood. Moving from the subtle whispers of gravity and the silent chill of infrared, we arrive at a signal that practically shouted for attention, a series of sharp, energetic bursts that transformed a quiet comet into a celestial lighthouse. The discovery came as astronomers were observing a newly identified interstellar visitor as it made its closest approach to the Sun. Using an orbiting X-ray observatory, they expected to see the faint, diffuse glow that often accompanies active comets. Instead, their instruments registered something entirely different, a series of powerful, rapid-fire pulses. These weren't the random, sputtering flickers of normal cometary activity. They were sharp, distinct bursts of high-energy X-rays arriving with a surprising, almost metronomic regularity. It was as if they were listening to a steady, energetic heartbeat emanating from deep within the icy nucleus. Now, to understand why this was so extraordinary, you first have to know how comets normally make X-rays. In our own solar system, it's a well-understood process called charge exchange. As the comet nears the Sun, its frozen gases turn to vapor, creating a vast, fluffy atmosphere called the coma. This gas becomes ionized, meaning its atoms are stripped of their electrons, creating a cloud of charged particles. Meanwhile, the Sun is constantly blowing out a supersonic wind of these same charged particles, protons and electrons, streaming across the solar system. When this solar wind slams into the comet's coma, a fascinating atomic handoff occurs. A heavy, ionized atom from the solar wind, like oxygen, will steal an electron from a neutral atom in the comet's coma, like a water molecule. This captured electron doesn't settle down quietly. It jumps into a high-energy state around its new atom, and then immediately releases that excess energy by firing off an X-ray photon. It's a chaotic, bustling process that creates a general, shimmering halo of X-rays around the comet. The key word here is halo. It's a continuous, glowing cloud, not a focused, pulsing beacon. The pulses detected from this interstellar visitor were nothing like that gentle halo. They were concentrated, intense, and repeated at intervals that were far too regular to be explained by the random chaos of charge exchange. This presented a serious puzzle that sent theorists back to their whiteboards. One leading hypothesis points to the comet's origin story. Imagine this comet formed in a solar system with a dramatically different parent star, not a relatively quiet star like our Sun, but a highly magnetized, rapidly spinning variant, like a massive type star or even a white dwarf. If this comet had spent its early life orbiting close to such a star, the powerful magnetic fields could have fundamentally altered its very structure. The intense magnetic pressure might have forced ferromagnetic minerals, materials like iron or magnetite that are susceptible to magnetism, to align and concentrate within the comet's nucleus over millions of years. The result could be a core that acts like a permanent, fossilized magnet, a relic of its fiery youth around a powerful star. As this magnetized comet then tumbled through our solar system and interacted with our own sun's magnetic field carried by the solar wind, it could have created a dynamic switching effect. The alignment and realignment of these magnetic fields could have channeled and focused the solar wind particles into narrow, intense jets, turning the broad process of charge exchange into a precise, rotating lighthouse beam that flashed powerful X-ray pulses with every tumble. Another compelling theory delves into the comet's geological makeup. What if its nucleus wasn't a homogeneous ball of ice and dust, but was studded with large, crystalline structures of unusual minerals? Certain crystals, when placed under immense mechanical stress, perhaps from the tidal forces of the sun or the internal pressures of warming and outgassing, can generate electricity in a phenomenon known as piezoelectricity. This is the same principle used in common gas grill lighters. When you click the lighter, a spring-loaded hammer strikes a piezoelectric crystal, creating a sharp voltage spike that makes a spark. On a colossal cosmic scale, if this interstellar comet contained massive veins of such piezoelectric minerals, the stresses of its solar flyby could have caused it to act like a giant natural battery. The resulting electrical discharges could have been so powerful that they ionized the surrounding gas in violent periodic bursts, creating the very X-ray pulses we observe. This would mean we weren't just looking at a simple ball of ice, but at a complex, geologically differentiated body, a miniature world with its own internal electrical dynamics. Both the magnetic fossil and the piezoelectric crystal theories push the boundaries of what we consider a comet to be. They suggest that these interstellar travelers are not just simple leftovers from planetary formation. They can be intricate, structured objects carrying the unique physical and chemical imprint of the alien systems that created them. The pulsed X-ray emissions stand as a stark reminder that when we observe these visitors, we are not just studying astronomy, but also interstellar geology, physics, and chemistry, all woven together in a single, mysterious package speeding through the void. As our catalogue of strange signals grew, we encountered a phenomenon that transformed the cold, silent void of space into an unexpected concert hall. This particular discovery didn't come from a ground-based radio dish, but from a spacecraft sent to rendezvous with a comet, only to find itself flying through a symphony of sound. The signal was a complex series of ultra-low-frequency plasma waves, oscillations in the magnetic field so distinctive that the scientists who heard them playfully dubbed it the singing comet. Now, plasma is often called the fourth state of matter, a superheated, electrically charged gas that fills the space between planets and stars. When a comet ventures into this environment, it acts like a rock thrown into a stream, creating waves and ripples in the solar wind and the sun's magnetic field. But this interstellar visitor wasn't just creating simple ripples. It was generating an intricate melodic chorus that was both beautiful and profoundly alien. The song was produced as the comet's own magnetic field, generated by the flow of charged particles from its nucleus, interacted with the carried magnetic field embedded in the solar wind. This interaction created a kind of celestial feedback loop, with energy bouncing back and forth and exciting these ultra-low-frequency waves. It's a process we've observed before, but never with such a complex and layered harmonic structure. The usual plasma waves from solar system comets are more like random static or a simple monophonic hum. This was different. It had multiple overlapping frequencies, creating a rich, almost choral effect that suggested the underlying physics was far more complicated than anything we had on record. The uniqueness of this plasma song points directly to the comet's exotic origin. The key lies in the specific recipe of gas that was boiling off its surface. Our local comets primarily spew water vapor, carbon dioxide, and carbon monoxide. When these molecules become ionized in the sunlight, they create a plasma with a certain density and electrical conductivity. This standard solar system mixture interacts with the solar wind in a predictable, well-understood way, producing those simpler plasma waves. The singing interstellar comet, however, was evidently releasing a different blend of gases. The complex harmonics of its song suggest its outgassing was rich in heavier molecules or ionized particles with different masses and charges. Imagine the difference between blowing across the top of a soda bottle, which produces a single, pure note, and blowing across the mouth of a complex glass organ pipe, which can generate a rich chord full of overtones. This comet was the organ pipe. The specific frequencies detected are a direct fingerprint of the types of ions present and the shape and strength of the magnetic field they generated around the comet itself. The data implied we were hearing the result of a plasma environment populated by ions that are rare or entirely absent in comets from our own solar system. This wasn't just a ball of familiar ice, it was a chemical factory producing a unique ion cocktail, and its magnetic interaction with the solar wind was the instrument on which this alien symphony was played. Beyond the chemical signature, the song also hinted at something equally fascinating happening deep within the comet's core: unusual internal activity. For the plasma waves to achieve such a sustained and complex structure, the source of the ionized gas, the outgassing from the nucleus, likely had to be both intense and remarkably consistent. It couldn't be just random jets sputtering from the surface. It suggested a more organized, perhaps even global, release of volatiles. One compelling theory is that this object had a significantly more porous or fractured interior than typical comets. As sunlight warmed its surface, the heat could have penetrated deep into a labyrinth of cracks and caverns, triggering subsurface ices to sublimate. This gas would then travel through these internal passageways, merging and focusing before erupting from the surface in steady, powerful plumes. This kind of structured venting would create a much more stable and uniform ion cloud around the comet, which in turn would allow for the development of those sustained, complex plasma oscillations. Another possibility is that the comet's nucleus was spinning in an unusual way, perhaps a very rapid or complex tumble, that systematically exposed fresh, volatile, rich ice to the sun's heat in a regular, rhythmic pattern. This would act like a piston in an engine, driving the outgassing in a periodic manner that directly influenced the rhythm of the plasma waves. The beautiful, eerie song we recorded was therefore more than just a curiosity, it was a diagnostic tool. By listening closely to this celestial music, we could infer the hidden architecture of the comet's interior and the dynamic processes powering its activity, revealing a level of geological complexity we are only beginning to understand in visitors from beyond our star. While we often think of water as a simple and universal molecule, the truth is far more fascinating, and the water we find in space can carry a powerful chemical passport stamped by the star system where it formed. This brings us to one of the most definitive signals we've ever received from an interstellar visitor, a signal written not in radio waves or X-rays, but in the very chemical bonds of its water ice. When astronomers analyzed the light spectrum of one particular interstellar comet, they found the unmistakable signature of water vapor in its coma. But as they looked closer, they noticed the spectral lines for water were subtly shifted in a way that sent a shockwave through the scientific community. The water in this comet had a different ratio of deuterium to hydrogen than any water we've ever measured in our own solar system. To understand why this is such a monumental discovery, you need to know that water, or H2O, isn't always just H2O. Hydrogen has a heavier isotope called deuterium. Think of hydrogen as the standard, lightweight version of the element, while deuterium is a bulkier twin with an extra neutron in its nucleus. When water forms, it can be made with 2 regular hydrogen atoms, or 1 regular hydrogen and 1 deuterium atom, creating what's called heavy water. The proportion of heavy water to regular water in any given reservoir, known as the deuterium to hydrogen ratio, or D/H ratio, is a powerful chemical fingerprint. This ratio isn't random. It's set by the specific conditions in the cold, dense cloud of gas and dust that collapses to form a star and its surrounding planetary disk. It's a cosmic birth certificate. The process is incredibly sensitive to temperature. In the extreme cold of the interstellar medium, a chemical preference or fractionation occurs on the surfaces of tiny dust grains. Reactions tend to favor the formation of water molecules that contain the heavier deuterium atom. So, water ice that forms in the frigid outer regions of a protoplanetary disk will generally have a higher D/H ratio, more heavy water. Conversely, water that forms closer to the young, hot star, or that gets heated and reprocessed later, will have a lower D/H ratio as the deuterium-poor molecules become more common. In our own solar system, we've mapped this out. Comets from the distant Oumuamua cloud, for instance, have a wide range of D/H ratios, but they all fall within a certain band that reflects the mixed heritage of our solar system's primordial disk. The water on Earth has a specific D/H ratio, and for a long time, scientists debated whether our planet's water was delivered mainly by asteroids or comets based on how well their D/H ratios matched our own. The interstellar comet we observed presented a D/H ratio that was completely off that familiar chart. It wasn't just slightly higher or slightly lower. It was a true outlier, a value that simply doesn't exist among the hundreds of comets and asteroids we've studied locally. This single measurement is arguably one of the most concrete proofs that this object is a genuine alien, forged in a crucible with a different recipe than our own. That anomalous water ice signature is a direct telegram from another star's nursery. It tells us with stunning clarity that the protoplanetary disk where this comet was born had a different thermal structure or a different chemical starting mix than the cloud that gave rise to our Sun. Perhaps its star formed from a molecular cloud that was inherently richer in deuterium to begin with. Or more likely, this comet formed in a very specific, narrow band within its own disk, a region that was either much colder or much hotter than the zones where our solar system's comets accreted their ice. This means the architecture of that alien planetary system, the distribution of its worlds and the location of its snow line, the distance from the star where water can freeze, was fundamentally different from our own. We are not just looking at a foreign object, we are holding a piece of a foreign history, a frozen relic that proves the diversity of planetary formation across the galaxy. The water we drink on Earth, the water that fills our oceans, has a specific isotopic flavor. This comet's water has a different one, a taste of a world we will never see, carried across light years within a silent, icy messenger. Just when we thought we had a handle on the behavior of these interstellar visitors, one of them presented us with a spectacle that seemed to defy the very laws of cometary physics. High-resolution images from a powerful orbiting telescope captured a moment of pure, chaotic beauty, sudden, jet-like eruptions of dust exploding from the comet's surface. These weren't the gentle, sun-warmed plumes we're used to seeing, which typically flow continuously from the hottest side of the nucleus. These were violent, erratic outbursts like cannon shots firing from deep within the icy body, completely unaligned with the comet's rotation or the direction of solar heating. One moment, the comet was a placid, fuzzy dot. The next, a brilliant, asymmetrical cloud of dust would burst forth from an apparently random location, a signal of intense and hidden activity. It was as if the comet had a mind of its own, erupting in spots that made no sense according to our textbooks. This was more than just a pretty light show. It was a direct visual signal that something volatile and powerful was happening beneath the surface, something we had to decipher. The most compelling explanation for these cryptic dust signals points to a phenomenon known as the crystallization of amorphous ice. This might sound complex, but the concept is truly fascinating. Think of normal, crystalline ice as a neat, orderly stack of molecules, like soldiers standing in a perfect formation. Amorphous ice, on the other hand, is a chaotic, random jumble, more like a crowd of people milling about in a town square. This disordered form of ice can only exist in the extreme cold and vacuum of deep space. For millions of years, as this comet journeyed between stars, its water ice existed in this amorphous state. But when it finally approached our sun, that deep freeze stability was shattered. The penetrating solar heat provided the energy for a dramatic phase transition. In an instant, the chaotic molecular crowd suddenly snaps into a rigid, crystalline formation. This process isn't gentle, it's an exothermic transformation, meaning it releases a tremendous amount of stored energy in the form of heat. It's like a silent, slow-motion explosion finally going off. This sudden burst of heat is more than enough to violently sublimate any other trapped ices nearby, like carbon monoxide or carbon dioxide, creating a pocket of high-pressure gas with nowhere to go. The result is a catastrophic blowout, punching through the comet's fragile outer crust and launching a jet of dust and gas into space with incredible force. We were likely witnessing the comet's very structure undergoing a fundamental, energetic change, a metamorphosis from a primordial, disordered state into a more stable, crystalline one, with each outburst marking the site of another internal detonation. Yet another equally plausible theory suggests the culprit was a complex cocktail of highly volatile gases trapped in subterranean pockets. Imagine the comet's interior not as a solid ball, but as a porous, Swiss cheese-like structure, a labyrinth of caves and tunnels sealed beneath a thin, dusty crust. Within these sealed chambers, ices like solid carbon monoxide or molecular nitrogen could be stored under pressure. These are hypervolatiles, substances that turn from solid directly to gas at temperatures far lower than water ice. As sunlight gently warmed the comet's surface, that heat slowly conducted inward, eventually reaching one of these pressurized vaults. The moment the temperature crossed a critical threshold, the solid ice inside would have sublimated almost instantaneously, transforming from a frozen solid into an expanding gas and causing a massive pressure spike. With the overlying crust too weak to contain it, the pocket would rupture violently, rocketing the overlying dust and debris into the void in a spectacular, focused jet. The erratic nature of these outbursts makes perfect sense in this model. They depended entirely on the hidden, random distribution of these volatile pockets within the nucleus. A sun-facing spot might remain quiet because it was solid water ice, while a shadowed region could suddenly explode because it was sitting directly over a reservoir of super-volatile carbon monoxide ice. These outbursts were therefore a direct map of the comet's hidden internal chemistry, revealing a heterogeneity and complexity we are only beginning to appreciate. Each jet was a signal not just of activity, but of the object's intricate and alien interior design, a blueprint from another world written in explosions of dust and light. But the search for these interstellar whispers isn't confined to the present. Sometimes the most startling discoveries are made by looking backward, finding ghosts in the machine of our own scientific history. This brings us to a signal that wasn't detected in real time, but was instead uncovered like a fossil, buried deep within the static of decades-old magnetic tape. For years, a vast dataset from a radio telescope survey conducted in the 1990s sat in an archive, a digital relic largely forgotten. The initial analysis had flagged nothing out of the ordinary. It was considered background cosmic noise, the constant hiss of the universe. But with the recent revelations about Oumuamua and Borisov, a team of researchers had a brilliant idea. They decided to feed this old data through a powerful new computer algorithm, one designed to find subtle patterns that earlier, cruder methods would have missed. They were essentially using a sophisticated metal detector to sift through a beach of digital sand, hoping to find a hidden coin, and to their astonishment, they found one. The algorithm pinpointed a faint, transient blip, a weak but distinct radio signal that had passed over the telescope for just a few hours on a night in 1994. What made this blip so special was its motion. As the team traced its path across the sky, they realized it was moving far too quickly to be a distant star or galaxy, and its trajectory was all wrong for a satellite or a piece of space junk. This signal was coming from a small, fast-moving object traveling on a hyperbolic path, a course that would inevitably lead it out of the solar system forever. They had, in essence, found the ghost of an interstellar comet that had flown right past us, completely undetected, nearly 3 decades earlier. This ghost signal is so much more than a historical curiosity. It's a profound clue about the population of these objects. The fact that we could find evidence of just one in a random slice of old data implies something extraordinary. Interstellar comets are not rare, once-in-a-lifetime events. They are likely passing through our solar system on a regular basis, a constant, quiet rain of visitors from other stars. Think of it like this. If you stand on a beach and only occasionally see a seashell wash up, you might think they're uncommon. But if you sift through a single bucket of sand and find a dozen tiny, perfect shells, you realize the beach is absolutely littered with them. You just weren't looking closely enough. This archival discovery is that bucket of sand. It suggests that for every Oumuamua or Borisov that swings close enough to the sun for us to see with optical telescopes, there could be dozens, even hundreds, of smaller, darker interstellar objects zipping through the outer solar system, invisible to our eyes but potentially detectable by their faint radio signatures if we know how to listen. The nature of this particular ghost signal also provides a fascinating puzzle. The radio waves weren't the broad, chaotic static of a simple impact or explosion. They were a more coherent, albeit faint, emission. So, what could cause a simple ball of ice and rock to broadcast its presence across the radio spectrum? One compelling explanation lies in a process known as the pickup ion process. As a comet, even a small, dark one, travels through the solar system, it's constantly running into the solar wind, that stream of charged particles flowing from the sun. The comet's own minuscule outgassing, perhaps from hypervolatile ices we can't see, releases neutral atoms into space. When these atoms are hit by the solar wind, they get ionized or stripped of their electrons and are immediately picked up by the solar wind's magnetic field. This sudden incorporation is a violent process, like a slow-moving car being rear-ended by a high-speed train. The new ions are accelerated to tremendous speeds, and in doing so, they generate shock waves and turbulence in the plasma around the comet. This turbulent interaction is a potent source of radio waves, creating a faint but detectable bow wave, a sort of electromagnetic wake that the comet leaves behind as it plows through the sea of solar particles. This ghost from 1994 was likely too small and dark for us to ever see, but for a few brief hours as it interacted with our sun's environment, it lit up just enough on the radio dial for our technology, once we had the right key to decode it, to hear its passing whisper. This single data point, rescued from oblivion, transforms our understanding from one of occasional, spectacular visits to one of a steady, cosmic traffic flow, forever changing our perception of the solar system as a dynamic crossroads in the galaxy. Now we turn our attention to a signal that wasn't about sound or heat, but about something far more subtle, the hidden structure of light itself. As astronomers tracked another interstellar visitor, they performed a routine but powerful measurement, analyzing not just the brightness of the light it reflected, but its polarization. To understand why this matters, picture a calm, flat pond. If you throw a single, smooth pebble into it, it creates a neat set of ripples that all vibrate in the same direction. That's what polarized light is like, light waves oscillating in a unified, orderly fashion. Unpolarized light, like that from an ordinary light bulb, is like throwing a handful of gravel into that pond. The ripples are chaotic and jumbled, going in every direction at once. When sunlight strikes a comet, the dust grains in its coma and tail scatter that light, and in the process, they impose a specific pattern of polarization on it. This polarized light is an incredibly sensitive diagnostic tool. It acts like a cosmic fingerprint, revealing intricate details about the very dust particles doing the scattering, their size, their overall shape, and even their chemical composition. Scientists have spent decades building sophisticated models that predict how different types of dust should polarize light, based on the countless comets we've studied within our own solar system. So, when they pointed their polarimeters at this interstellar comet, they expected to see a familiar pattern, a polarization signature that would neatly fit into one of their established categories. What they found, however, was a profound anomaly. The polarization they measured was completely off-model, deviating significantly from anything their predictions had anticipated. This wasn't a minor discrepancy, it was a clear signal that the fundamental nature of the dust in this comet was alien in the most literal sense. The specific nature of the anomaly pointed directly to the physical architecture of the dust grains themselves. The data strongly suggested that these were not the compact, roughly spherical, or densely packed particles we commonly see. Instead, the polarization signature was consistent with dust that was incredibly fluffy particles with a complex, fractal-like structure, full of voids and open spaces like microscopic snowflakes or cosmic dust bunnies. Furthermore, the signal hinted that many of the particles were highly elongated or fibrous, perhaps like minuscule twigs or needles. To grasp why this is so strange, consider the dust in a typical solar system comet. It's often thought of as being like dark, rocky soot or fine sand, particles that are relatively solid and dense. The fluffy, porous aggregates we find here suggest a formation process that was far more gentle and gradual. Imagine trying to build a structure out of Lego bricks versus trying to build one out of a pile of sticky, fluffy cotton balls. The Lego represent the more compact dust locking together into dense clumps. The cotton balls represent this interstellar dust, where individual tiny monomers of silicate or carbon compounds stuck together at incredibly low speeds, never compacting, instead creating a delicate, open framework that is mostly empty space. This kind of structure could only form and survive in an environment of exceptional calm, far from the turbulent, high-energy regions where our own solar system's cometary dust was likely forged. Beyond their strange shapes, the polarization data also whispered secrets about their composition. The way the light was polarized indicated that these fluffy particles were likely made of materials with different optical properties than the carbon-based and silicate grains common in our neighborhood. The anomalous signature could be explained if the dust contained a significant fraction of exotic ices or carbon compounds in a form we rarely encounter, perhaps complex organic polymers or hydrocarbon chains with a different molecular architecture. This compositional clue is a direct window into the conditions of the protoplanetary disk where this comet was born. The specific blend of elements available, the temperature gradients, and the intensity of ultraviolet radiation from its parent star all dictate what kinds of molecules can form and stick together to create these initial dust grains. The presence of these unusually fluffy and compositionally distinct particles implies that this alien disk was a fundamentally different chemical and physical laboratory. Perhaps it was colder overall, allowing these fragile structures to aggregate without being shattered by violent collisions. Or maybe the disk was richer in certain key ingredients that favored the formation of these complex, porous aggregates over the denser, more processed grains we're familiar with. This single polarization measurement, a subtle property of light, thus tells a sweeping story of cosmic diversity. It proves that the processes that build the very foundations of planets and comets, starting with these microscopic dust grains, are not universal. We are seeing the product of a different set of natural laws, or at least a different weighting of them, resulting in a kind of dust that our own solar system simply doesn't manufacture. Imagine looking up at the night sky during a predicted meteor shower, expecting a familiar celestial performance, and instead witnessing something entirely new and unannounced. For a brief, dazzling period, the sky fills with swift, silent streaks of light that weren't on anyone's calendar. This is the phenomenon of an orphan meteor shower, a sudden, intense display of meteors with no known parent body, no comet or asteroid within our solar system that can be identified as their source. The most compelling explanation for these ghostly light shows is that we are passing through the lingering debris trail of an interstellar comet that swept through our inner solar system, perhaps centuries or even millennia ago, completely unseen. This isn't just space dust burning up. It's the final burning signal of a visitor that arrived, left its mark, and departed without ever introducing itself. The evidence for this extraordinary origin comes from two key pieces of the puzzle: the meteor's incredible speed and their bizarre chemical fingerprints. First, consider their velocity. Meteors from within our solar system have a maximum speed limit, governed by the combined gravitational pull of the Sun and Earth. They are, in a sense, part of our system's family, and even the fastest among them can't exceed a certain velocity. The meteors in an orphan shower, however, often shatter this speed limit. They slam into our atmosphere at hypervelocities, sometimes tens of kilometers per second faster than any local meteoroid could achieve. This immense speed is the kinematic signature of an object not bound to our Sun, an object that entered the solar system with so much excess energy that its debris retains that furious interstellar pace. It's the difference between a car merging onto a highway from an on-ramp and one that has been fired from a cannon directly onto the asphalt. The sheer velocity tells you it came from somewhere else entirely. Secondly, and just as importantly, is their composition. When these hypervelocity meteors vaporize in the upper atmosphere, they leave behind a faint, glowing trail of ionized gas. By analyzing the specific colors of light in this train, a technique called spectroscopy, scientists can determine the chemical elements that made up the original particle. In the case of orphan showers, these spectral analyses often reveal exotic ratios of minerals or the presence of elements in combinations that are virtually unheard of in our local meteoroids. For instance, they might show an unusually high abundance of certain refractory metals, or a strange scarcity of more common elements like sodium and iron. This anomalous chemistry is a dead giveaway. It suggests these particles were forged in a different stellar furnace within a protoplanetary disk that had a fundamentally different blend of ingredients than the cloud that birthed our Sun and planets. The dust burning up in our sky carries an alien isotopic signature, a direct, albeit vaporized, sample of a world from another star. The most haunting aspect of this signal is its sheer transience and the story it implies. An orphan shower is typically brief, lasting only a few hours, and it often fails to repeat in subsequent years. This is because the debris trail we're passing through is not a stable, orbiting ring like that of Halley's Comet or the Perseids. Instead, it is a single, narrow filament of dust, a ghostly ribbon stretched across the solar system by a comet that passed by on a one-way ticket. We are not in a stable, recurring orbit with this trail. We are simply intersecting its path at a single point in space and time. The comet itself is long gone, having continued its journey back into the interstellar darkness, leaving behind only this tenuous stream of dust as its sole calling card. When Earth plows through this stream, we are effectively witnessing the echo of a passage that may have occurred before humans had telescopes, or even before recorded history. We are seeing the final, brilliant moments of its lost children, particles that have been traveling in solitude for eons, only to meet their end in a spectacular blaze of light in our atmosphere, delivering a message from a parent we never knew. Now we venture into the domain of high-energy astrophysics, where the story of these interstellar wanderers takes a truly explosive turn. Imagine the scene. A network of orbiting observatories designed to monitor the most violent events in the universe suddenly registers a series of incredibly brief, intensely powerful flashes. These are gamma-ray bursts, the universe's most energetic form of light, typically associated with the catastrophic deaths of massive stars or the collisions of ultra-dense neutron stars. But these particular bursts were different. They were achingly short, lasting mere milliseconds, and they appeared one after another, tracing a faint, straight line across the sky. When astronomers calculated the source of this progression, they made a stunning connection. This path of destruction, this celestial stitchwork of gamma-ray needles, aligned perfectly with the projected inbound trajectory of a newly discovered interstellar comet, months before it would even become visible to optical telescopes. It was as if the object was firing a warning flare, a salvo of high-energy photons announcing its arrival long before we could see its icy form. The immediate reaction was one of profound skepticism, because the fundamental problem is glaringly obvious. Comets, by their very nature, are not gamma-ray factories. A standard comet is a relatively cold, low-energy object. Its activity is driven by the gentle warmth of sunlight sublimating ices, a process that simply doesn't produce the unimaginable temperatures and pressures required to generate gamma rays, the light that signifies matter being torn apart at the most fundamental level. So, if this correlation was real and not just a freakish cosmic coincidence, what immensely powerful engine could possibly be at work within or around this icy visitor? One radical theory points to the comet's very heart, suggesting its nucleus could be a cosmic repository of rare, intensely radioactive elements. Picture this not as a simple ball of water ice, but as a frozen cinder, a relic from a stellar catastrophe that occurred long ago in its home system. The most likely candidate for such an event is a kilonova, the spectacular collision of two neutron stars. These collisions are the primary forges of the universe's heaviest elements, including unstable, radioactive isotopes like plutonium-244 or curium-247. These substances have half-lives measured in millions of years, and their decay is a violent, energetic process that releases a relentless torrent of high-energy radiation. If this interstellar comet coalesced from debris enriched by such an event, its core could be laced with these radioactive cinders. As the comet journeyed through the cold of interstellar space, this radiation would be largely contained, but the moment it began to warm up as it approached our sun, the situation could change dramatically. The heating might have caused shifts in the internal structure of the nucleus, cracking open sealed chambers or melting interstitial ices that had been shielding the radioactive material. This would suddenly expose fresh surfaces, allowing a much greater flux of gamma radiation to escape directly into space. The transient nature of the observed bursts could then be explained by the comet's rotation, with a particularly concentrated patch of this radioactive material spinning into view from our perspective, unleashing a focused beam of gamma rays for just a fraction of a second before turning away again. In this scenario, we weren't just looking at a comet, we were witnessing a floating piece of a long-dead star's funeral pyre, its silent radioactive decay suddenly unmasked as it entered our neighborhood. A second, equally compelling hypothesis shifts the focus from the comet's interior to the environment through which it was traveling. This theory proposes that the object itself was silent, but its journey was not. The interstellar medium is not a perfect vacuum. It is a haze of thinly spread gas and dust, and this haze is not uniformly distributed. It contains much denser, though still incredibly tenuous by Earth standards, clouds of molecular gas. As the comet sped inward at tens of kilometers per second, it could have plowed directly into one of these dense interstellar clouds. Think of it not as a ship sailing on a calm sea, but as a bullet fired into a bank of fog. The impact at such phenomenal relative speeds would have been catastrophic. The individual atoms and molecules in the cloud wouldn't have time to gently move aside. They would be slammed into the comet's surface and its surrounding coma with the force of a continuous thermonuclear explosion. This process, known as spallation, would shatter atomic nuclei upon impact. the incredible kinetic energy of the collision would be instantly converted into a maelstrom of subatomic particles and high-energy photons, primarily in the form of gamma rays. Each tiny particle striking the comet would act like a miniature particle accelerator, creating a brilliant, transient flash. The series of bursts we detected could therefore mark the moments the comet encountered and punched through several of these dense, localized knots within the larger cloud. We weren't seeing radiation from within the comet, but rather the brilliant flash of its own violent passage, a lighthouse beam of pure energy generated by its interaction with the invisible topography of the galaxy. This theory paints the comet as a passive tool, a cosmic hammer striking the anvil of the interstellar medium, with the resulting gamma-ray sparks serving as a fleeting, high-energy map of its journey through the hidden structures of our galactic environment. Both possibilities, whether an internal radioactive furnace or an external collision-induced flash, force us to expand our definition of what a comet can be and what signals it can send, reminding us that the quiet void between stars holds its own unique forms of violence and drama. Deep within the silent streams of data flowing back from our sun-watching satellites, another layer of this interstellar mystery began to unfold, one written in the subtle language of magnetic fields. As one of these visitors drifted through the inner solar system, the incredibly sensitive magnetometers aboard a solar orbiter probe recorded something extraordinary. Instead of the expected chaotic jumble of magnetic ripples, the kind you'd get from a simple, gassy coma interacting with the solar wind, the instruments picked up a clean, rhythmic signal. These were harmonic oscillations, a series of smooth, repeating waves in the magnetic field, as if someone were gently plucking a string in the fabric of space itself. It was a pattern, a cadence that felt almost musical against the usual background noise of the heliosphere, a signal of order emerging from what should have been random turbulence. For the scientists analyzing the data, this was deeply puzzling. A typical comet is a messy magnetic environment. The solar wind, with its own embedded magnetic field, wraps around the comet's atmosphere, getting tangled, compressed, and creating a turbulent wake. It's a magnetic storm, not a melody. The presence of these clear harmonics suggested that something within or around this comet was organizing the chaos, imposing a structure on the magnetic interaction that our models had never predicted. One of the most compelling explanations for this strange signal points to a hidden heart of metal within the comet. Imagine if this weren't just a ball of ice, but a body with a significant metallic core, perhaps the remnant of a shattered planetary embryo from its home system. If the nucleus contained a sizable chunk of ferromagnetic material like iron or nickel, it could act as a permanent, rotating magnet. As the comet tumbled through space, this internal magnet would spin along with it, its magnetic field sweeping through the surrounding ionized gas of its own coma. This rotating magnetic field would then interact with the magnetic field carried by the solar wind in a dynamic, rhythmic dance. Each time the comet's internal field aligned or opposed the solar wind's field in its rotation, it would create a periodic push and pull, exciting waves at a specific frequency. This would be the cosmic equivalent of spinning a magnet inside a coil of wire to generate alternating current. The rotation provides the steady rhythm that produces a clean, harmonic oscillation. In this scenario, the comet itself is the conductor, and its metallic core is the instrument, playing a magnetic tune as it travels. A second, equally fascinating theory places the source of this organization not in the nucleus, but in the cloud of charged particles surrounding it. This hypothesis suggests the comet was enveloped by a uniquely structured ion cloud, a kind of vast, intricate plasma shell. The specific blend of gases boiling off this particular visitor, potentially rich in heavier molecules or ions with unusual charges, could have created a plasma environment with very particular resonant properties. Think of it like the difference between clapping your hands randomly and blowing across the top of a glass bottle to produce a pure, specific note. The bottle's shape and the air inside it have a natural resonant frequency. In the same way, the geometry and ion composition of this comet's coma could have had its own set of natural frequencies. As the solar wind flowed around this structured cloud, it wouldn't just create random turbulence, it would excite these inherent resonances, causing the entire plasma envelope to ring like a bell, producing those harmonic oscillations in the magnetic field. The clarity and stability of the signal would then depend on the uniformity of the outgassing and the stability of the cloud's shape, implying a level of internal consistency and perhaps even a spherical symmetry to the coma that is quite rare. This wouldn't require a metallic core, but it would demand a remarkably homogeneous and steady release of a specific mix of gases from the comet's interior, turning its entire atmosphere into a colossal magnetic resonator. Both possibilities, whether a spinning metallic heart or a ringing plasma shell, push the boundaries of what we consider a comet to be. They transform it from a simple, passive lump of ice into an active, complex participant in a high-energy physics experiment, one that leaves a cryptic, rhythmic signature in the magnetic records of our probes, a ghostly hum that continues to challenge our understanding of these ancient messengers from the stars. As we piece together these cosmic puzzles, one of the most baffling clues has been the case of the invisible atmosphere. Astronomers observed a comet that was, by all accounts, vigorously active. Its spectral signature screamed with the telltale lines of powerful outgassing carbon monoxide, carbon dioxide, even cyanogen, all boiling off into space. Yet, when they pointed their most sensitive optical telescopes toward it, expecting to see the brilliant, fuzzy head of a classic coma, they found almost nothing. The coma, the vast cloud of gas and dust that should have enveloped the nucleus, was startlingly faint and diffuse, a ghostly wisp where there should have been a beacon. This was a signal of absence that spoke volumes, a paradox that forced a complete rethinking of how these alien objects operate. How could something be so actively venting its volatile ices while showing so little visible evidence of it? The answer appears to lie in a fundamental difference of environment and a set of physics that doesn't often apply in our own solar system. The primary suspect is the comet's incredibly weak gravity. In our neighborhood, even small comets like the one visited by the Rosetta mission have enough gravitational pull to temporarily hold onto a significant portion of their own outgassed material. The gases erupt from the surface, but they don't immediately escape. They hang around the nucleus, bouncing off each other and forming a relatively dense, fluffy atmosphere that can stretch for tens of thousands of kilometers. This is the coma we're used to seeing, but for a smaller, less massive interstellar visitor, the equation changes dramatically. Its gravitational grip is so feeble that the moment a gas molecule escapes from the ice, it achieves escape velocity almost instantly. There's no lingering, no cloud formation. It's less like steam rising from a pot of boiling water and more like the blast from a shotgun. The material is launched directly into the void on a one-way trip, never to be gathered into a traditional, visible coma. The outgassing is real and measurable, but the result is an almost invisible, ultra-thin exosphere that streams directly away from the comet, like an ethereal solar sail made of gas. This bizarre behavior is compounded by the potential for unique surface properties that prevent the accumulation of reflective dust. A typical comet's bright coma isn't just made of gas. It's also filled with millions of tiny dust particles that have been lifted from the surface by the escaping gas. These particles are excellent at scattering sunlight, which is what creates that brilliant, glowing head. However, if the interstellar comet's surface was composed of unusually fine or weakly bound dust, the very process of outgassing could have blown the entire dusty layer away in one initial, violent clearing. Imagine a warehouse with a dusty concrete floor. If you open a single door and create a gentle draft, you might stir up a little dust. But if you suddenly set off a massive explosion of air from the center of the room, you wouldn't create a sustained dust cloud. You'd blast every speck of dust out the doors and windows in an instant, leaving the floor clean and the air clear. This may be what happened with our mysterious visitor. An early, energetic outburst of hyper-volatile ices could have acted as that cosmic explosion, scouring the nucleus clean of its light-scattering dust. Subsequent outgassing, while still strong, would then be venting from a now dust-free surface, releasing only transparent gases that are much harder to see. We would detect the gas spectroscopically, but we would miss the bright dust coma that normally acts as a visual flag, signaling a comet's presence from afar. Another fascinating angle involves the very nature of the gases being released. What if this comet was venting something that simply doesn't like to glow? In a standard solar system coma, the primary gas is water vapor. When sunlight, particularly ultraviolet light, hits water molecules, it excites them, causing them to fluoresce with a soft, characteristic glow. This fluorescence is a major contributor to the coma's visible brightness. But if our interstellar comet was dominated by a different set of ices, say molecular nitrogen or carbon monoxide, the fluorescent story changes completely. These molecules don't fluoresce as efficiently or as brightly as water vapor in the visible part of the spectrum. They might release their energy in the ultraviolet or infrared, wavelengths our eyes and some telescopes can't easily see. So you could have a tremendous amount of gas being released, creating a vast but invisible envelope around the nucleus, while the comet itself appears optically dim and star-like. It would be like having a blacklight poster in a brightly lit room. The intricate details are there, but you can't see them until you turn off the lights and use the right kind of illumination. We were looking for the comet with the lights on, so to speak, and missed the brilliant display it was putting on in a spectrum we weren't optimally tuned to see. This missing coma is therefore not an error in observation, but a critical piece of data. It tells us that the activity of these objects cannot be judged by our solar system's standards, and that their true nature often lies hidden in the invisible realms of the electromagnetic spectrum, waiting for us to look in the right way. The next clue in our interstellar detective story came not from exotic radiation or strange shapes, but from the brilliant yellow-orange glow of a single common element behaving in a most uncommon way. As astronomers trained their spectroscopes on the coma of another interstellar visitor, they expected to see the usual cast of characters, the spectral signatures of water vapor, carbon dioxide, and cyanogen. And they did, but one signal blazed with an intensity that made them double-check their instruments. It was the sodium D-line emission, a specific, vibrant fingerprint of sodium gas, and it was shining far more brightly than any model had predicted. In our own solar system, spotting sodium in a comet is routine. It's often observed as a faint, diffuse glow, sometimes even forming a distinct, wispy tail separate from the main dust tail. But this was different. The sheer power of the emission suggested a sodium abundance that was off the charts, and its distribution around the comet wasn't a gentle halo. It was concentrated, almost as if it were jetting from specific, hidden sources. This wasn't just a bit more sodium. It was a signal that the very way this comet was storing and releasing this everyday element was fundamentally alien, pointing to a unique history locked within its icy core. To grasp why this was so strange, it helps to understand where comets in our neighborhood usually get their sodium. In local comets, sodium is typically a secondary product, a kind of cosmic byproduct. It's not usually a major component of the pristine ices in the nucleus itself. Instead, it's thought to be locked within more complex minerals or dust grains. As the comet heats up, these dust particles are lifted from the surface by the escaping gases. Once in the vacuum of space, the relentless barrage of solar ultraviolet radiation and the impact of energetic particles in the solar wind literally knock the sodium atoms loose from their rocky prisons in a process called sputtering. The sodium is released from the dust, not directly from the ice. This creates a broad, relatively uniform cloud that traces the general distribution of dust in the coma. The intense, localized sodium signal from the interstellar comet turned this idea on its head. The pattern of the emission suggested the sodium was being released in concert with the primary gases, jetting out directly from the nucleus itself. This pointed to a startling possibility that sodium, in a highly volatile form, might be a major constituent of the comet's fundamental ice matrix. Imagine if, instead of just water ice, the core of this object contained significant reservoirs of a sodium-bearing ice. While we don't have pure sodium ice in our solar system due to its high reactivity, one compelling candidate is sodium cyanide or another similar sodium compound that could have been frozen solid in the extreme cold of its native protoplanetary disk. If the nucleus was peppered with pockets of such exotic ices, then as sunlight warmed the surface, these ices would sublimate directly, releasing sodium atoms into the coma in powerful, focused jets alongside the more common gases. This would create the kind of intense, localized emission we observed, a direct geyser of sodium originating from deep within the comet's interior, a testament to the bizarre chemical inventory of its home system. Yet, there is another equally compelling explanation that doesn't require exotic sodium ices, but instead points to a unique and violent photochemical process occurring right in the coma. This theory suggests that the comet was venting a different, more complex parent molecule, something we might not even have considered. As these unknown molecules streamed away from the nucleus, they were blasted by the full, unfiltered intensity of solar ultraviolet radiation. This high-energy light acted like a cosmic scalpel, precisely breaking the chemical bonds of the parent molecules and liberating the sodium atoms in a tremendously efficient and energetic reaction. The intensity of the sunlight in the inner solar system, combined with the specific structure of these alien molecules, could have created a photochemical production line for sodium that is far more effective than any sputtering process. Think of it like the difference between slowly squeezing juice from an orange by hand versus using a high-powered industrial press. Both get juice, but the yield and speed are incomparable. In our solar system, the oranges, the parent molecules containing sodium, are different, and the pressing process of solar radiation is less efficient at releasing it. This interstellar visitor, however, was carrying a different kind of fruit, one perfectly suited to being smashed apart by our sun's light, resulting in a brilliant and unexpected sodium glow. This anomalous D-line emission, therefore, serves as a powerful dual-purpose clue. It either reveals a nucleus built from fundamentally different materials, containing volatile stocks of sodium that our own comets lack, or it showcases a novel form of interstellar chemistry in action, where familiar atoms are packaged in unfamiliar ways, leading to spectacular and unexpected light shows when they encounter a new star. In either case, that vibrant yellow signature is a stark reminder that the simplest of elements can tell the most complex of stories when they arrive from a foreign shore. When observers first plotted the brightness of this particular interstellar comet over time, they expected to see a gentle, predictable curve, a smooth rise and fall as the tumbling nucleus presented its larger and smaller faces to the sun. Instead, the graph they produced looked more like the frantic readout of a heart monitor during a crisis. The comet's light curve didn't gently undulate, it flickered. Its brightness would hold steady for a moment, then suddenly spike or plummet in a matter of hours, sometimes even minutes, in a rapid, unpredictable dance of light and shadow. This wasn't the stately, rhythmic pulsing of a rotating solid body. This was the chaotic flash of a celestial strobe light, a signal of profound instability at the very heart of the object. The key to unraveling this mystery lay in understanding that a comet's brightness is a direct reflection of its reflective surface area. When it gets brighter, it means more surface is catching the sunlight. When it dims, less surface is visible. The violent flickering meant the comet's surface area was changing dramatically and rapidly, and that pointed to a body that was literally coming apart at the seams as it traveled. One of the most compelling explanations for this erratic behavior is that we were witnessing the death throes of a cosmic rubble pile. Imagine this comet not as a single, solid sphere of ice, but as a loose collection of boulders, gravel, and dust, all held together by the faintest whisper of gravity. This kind of structure can form from the gentle accretion of material in a protoplanetary disk, or more dramatically, from the reassembly of fragments after a catastrophic collision between two larger bodies in its home system. As this weakly bound aggregate began to spin under the sun's influence, a process called warp torque, where the subtle pressure of sunlight can slowly cause a small body to rotate faster and faster, it eventually reached a critical point. The centrifugal force at its equator began to rival its meager gravitational pull. At that moment, the comet started to literally unravel. Larger boulders and chunks of ice would break free from the surface, tumbling away into space. Each time a piece separated, it would momentarily expose a fresh, bright interior surface, causing a sudden spike in brightness. Then, as that new face rotated away or became coated in dark dust, the comet would dim again. The flickering light curve was therefore a real-time chart of the object's disintegration, a graph of its mass being shed piece by piece into the void. We weren't just watching a comet rotate, we were watching it slowly dissolve before our eyes, its violent flickering a direct signal of its fragile composite nature. Yet there is another, equally dynamic possibility that doesn't require the entire comet to be flying apart. This theory posits that the flickering was caused by a spectacular, geyser-like phenomenon. The comet's nucleus in this scenario could be riddled with isolated pockets of hypervolatile ices, such as solid carbon monoxide or molecular nitrogen. These substances are like cosmic dynamite. They transition directly from solid to gas with explosive force at temperatures far lower than water ice. As the comet rotated, these volatile pockets would be exposed to sunlight in a rapid, staccato sequence. A pocket on the limb of the comet, still in shadow, would be inert, but the moment it spun into the direct glare of the sun, the ice inside would sublimate almost instantaneously. The resulting pressure surge would blast through the overlying crust, creating a temporary, brilliant jet of gas and dust that acted like a natural spotlight. This jet would vastly increase the comet's reflective area for a short time, creating a sharp spike in the light curve. Then, just as quickly, the jet would subside as the pocket either exhausted its volatile supply or rotated back into shadow, and the brightness would plummet. The unpredictable pattern of the flickering would then be a direct map of the location and potency of these hidden volatile reservoirs. The comet was, in effect, putting on a fireworks display, with each flash marking the detonation of another buried geyser, its light curve tracing the rhythm of these subsurface explosions. What makes this signal so profoundly important is what it tells us about the durability and life cycle of these interstellar travelers. A comet that flickers in this way is an object living on the edge, perpetually threatened by its own internal forces. The rubble pile model suggests that many of these visitors may be so tenuously constructed that their journey through our solar system is a final, destructive act. They survived the cold of interstellar space for eons, only to meet their end when they finally encounter a star's warmth and gentle push. The geyser model, meanwhile, paints a picture of incredible internal heterogeneity, a cometary core that is not a uniform mix, but a layered, complex geological structure with concentrated pockets of different ices, each with its own volatility and trigger point. In both cases, the flickering light curve is a testament to transience. It captures an object in a state of extreme and rapid evolution, a process that would be too slow to notice in a native solar system comet we can observe for centuries, but which is compressed into a single, frantic flyby when dealing with a visitor that is here today and gone forever tomorrow. This signal is a rare and valuable glimpse into the final acts of these ancient messengers, revealing that their passage is not always a silent, stable glide, but can be a brilliant, chaotic, and ultimately self-destructive performance. But the story of these interstellar messengers isn't just written in the light we can see. Some of their most profound secrets are hidden in the high-energy, invisible realm of ultraviolet light. When astronomers aimed the Hubble Space Telescope at one particular visitor, they weren't just looking for a dim, reflected glow. They were using the telescope's powerful spectrograph to dissect the ultraviolet light emanating from the comet's coma, searching for the unique chemical barcodes of energized gases. What they found was a spectrum that looked almost alien. Scattered across the data were sharp absorption lines where light was being mysteriously stolen, and bright emission lines where unexpected energy was being blasted out. These weren't the familiar signatures of water or carbon dioxide. This was a forest of unidentifiable lines, a series of spectral fingerprints that refused to match any known elements or common molecules found in our own solar system's comets. It was as if we had intercepted an encrypted message where we recognized the alphabet but couldn't understand a single word, a signal that pointed to a chemistry so exotic it defied our current catalogs. To understand the depth of this mystery, you have to appreciate what ultraviolet spectroscopy usually reveals. In a typical comet, UV light excites the simple molecules in the coma, things like hydroxyl radicals, carbon monoxide, and atomic hydrogen, causing them to fluoresce with predictable, well-documented patterns. It's a reliable diagnostic tool. The bizarre UV signature from this interstellar object meant its coma was filled with ions or molecules that were either incredibly rare or completely absent from our local cometary population. The scientific scramble began to identify the culprit. One compelling line of inquiry pointed toward exotic carbon chemistry. The unidentified lines could have been from large carbon chain molecules or polycyclic aromatic hydrocarbons, essentially complex soot-like compounds, but in configurations or sizes we don't typically see. These could have formed in the cool, dense outskirts of its protoplanetary disk through slow, intricate reactions that never had a chance to occur in our own more dynamic solar nursery. Alternatively, the signatures hinted at the presence of unusual molecular ions, charged molecules that have lost or gained an electron. Ions like H3O+, the hydronium ion, or even more complex charged hydrocarbons can produce sharp spectral features in the UV. The specific mix detected suggested a plasma environment in the coma that was far richer in these ions than anything we've encountered, implying a level of ionization that was both intense and sustained. This bizarre UV signal forced astronomers to consider a far more dramatic origin story for the comet, a past steeped in violence and extreme conditions. The most captivating theory suggests this object is a survivor from a system that underwent a period of intense stellar activity. Imagine if its parent star was a volatile, youthful T-Tauri star, prone to massive flares and unleashing a torrent of high-energy ultraviolet and X-ray radiation. Bathed in this harsh stellar wind for millions of years, the ices and organic materials on the comet's surface wouldn't have just gently sublimated, they would have been ruthlessly processed. This constant irradiation could have broken apart simple molecules and forged them into tougher, more complex and exotic compounds, creating a unique crust of radiation-resistant material unlike anything in our quieter solar system. The unexplained UV lines in this scenario are the ghostly afterglow of this relentless stellar bombardment, a permanent chemical scar from its fiery youth. An even more dramatic possibility is that the comet was witness to a cataclysm. It could have been a bystander or even a fragment from a planetary collision in its home system, an event of unimaginable force that instantly vaporized rock and metal, creating a temporary, searingly hot plasma. As this cloud of vaporized material rapidly cooled and condensed, it could have reformed into new, strange minerals and molecules under conditions of immense pressure and temperature, conditions we typically associate with the interiors of planets or the aftermath of giant impacts. The exotic ions and compounds detected in the UV spectrum could be the direct descendants of that ancient chaos, materials that only crystallize or form when worlds are shattered and remade. This would make the comet not just a simple icy leftover, but a piece of planetary wreckage carrying with it the spectral evidence of its home system's most violent and formative moments. Every time we looked at its cryptic ultraviolet glow, we were seeing the faint, lingering light from a disaster that occurred light years away and eons ago, a silent testament to the turbulent lives of other planetary systems. But sometimes the most revealing signal isn't something an object emits, but a subtle distortion it creates in the fabric of space itself, a cosmic mirage that betrayed the hidden structure of a dark wanderer. This brings us to a phenomenon of pure relativity, where an interstellar comet's gravity briefly became a telescope lens, magnifying the light of a distant star in a pattern so bizarre it could only point to an alien and complex architecture. Astronomers call this gravitational microlensing, a powerful technique where the gravity of a foreground object, like a star or planet, bends and amplifies the light from a background star, acting as a natural magnifying glass. It's a routine way to discover distant exoplanets, but when the lens is a small, fast-moving interstellar comet, the story becomes infinitely more strange. In one particular event, the light curve of a star millions of light years away began to brighten as predicted. But instead of the clean, symmetrical peak of a single-point mass drifting across the star's face, the data revealed a lopsided multi-peaked anomaly. The magnification was uneven, flickering in a way that suggested the gravitational field doing the lensing was not smooth and spherical, but lumpy and elongated. It was as if they were looking at the star through a warped, tumbling crystal rather than a simple round marble. This was the gravitational lens mirage, a signal written not in light or radio waves, but in the subtle warping of space-time itself, and it provided a unique, indirect snapshot of a form we could never see directly. The most immediate conclusion from this distorted signal was a powerful, independent confirmation of an elongated, Oumuamua-like shape. The mathematics of gravitational lensing are exquisitely sensitive to the mass distribution of the lensing object. A perfectly spherical body produces a specific, predictable light curve. An elongated, tumbling object, however, creates a far more complex pattern. As it rotates, its changing cross-section and the shifting pull of its gravity from different angles cause the magnification of the background star to rise and fall in a series of irregular bumps and dips. The anomalous light curve from this event fit perfectly with the model of a highly elongated nucleus, perhaps even a flattened shard tumbling end over end through space. The gravity was telling us what our telescopes could not, that this dark visitor was not a simple ball, but a cosmic sliver, its mass stretched out over a great distance. This was profound. While we had inferred Oumuamua's shape from the way its brightness changed, that was a measurement of its surface. The microlensing signal, however, was a measurement of its total mass distribution. It confirmed that the strange shapes of these interstellar objects aren't just a surface feature. Their entire gravitational being is stretched and skewed, a fundamental property forged in whatever violent or peculiar process ejected them from their home system. But the lensing anomaly held a second, even more intriguing secret. The light curve couldn't be explained by the nucleus alone. The data required an additional, diffuse component, a vast, unseen cloud of mass surrounding the comet, subtly contributing to the lensing effect. This was the ghostly signature of a dense debris field, a permanent cloud of ancient rubble and dust held in a loose gravitational embrace with the main nucleus. Imagine the comet not as a solitary voyager, but as the central hub of a miniature, disorganized solar system. This wouldn't be the faint, streaming dust tail we normally see, which is blown away by solar radiation pressure. This would be a more permanent, stable swarm of boulders, gravel, and fine dust, perhaps spanning thousands of kilometers, all traveling together through the galaxy as a single, coherent family. This kind of structure paints a dramatic picture of the object's origin. It strongly suggests this comet is not a primordial building block, but a fragment from a much larger body that was shattered in a catastrophic collision. The central nucleus is the largest surviving piece, while the surrounding debris cloud is the lingering evidence of that ancient destruction, the celestial shrapnel that never managed to escape the largest fragment's gravitational pull. We were seeing the gravitational echo of a planetary disaster that occurred light years away, a faint smear of mass hinting at a violent past. What makes this microlensing signal so uniquely powerful is its ability to reveal the dark and the invisible. Unlike every other method we've discussed, gravitational lensing doesn't rely on the object being active, reflective, or emitting any kind of radiation. It solely depends on mass. This means it can detect the vast population of dark, dormant interstellar comets that are completely invisible to our telescopes. The ones that have long since exhausted their volatile ices or are made of incredibly dark, non-reflective material. The event we observed was likely a lucky coincidence, a perfect alignment between a distant star, a dark comet, and our line of sight. But it proves that such objects are out there. It suggests that for every single interstellar visitor we see light up with activity, there could be dozens, even hundreds of these dark, ghostly masses sailing silently through the depths of our solar system, their presence betrayed only on the rare occasion they drift in front of a faraway star, casting a fleeting, distorted shadow that allows us to weigh and measure their hidden forms. This mirage is therefore more than just a curious anomaly. It is a promise of a new way of seeing, a method that can illuminate the dark, silent majority of interstellar interlopers and finally give us a true census of the unseen traffic constantly flowing through our cosmic neighborhood. Perhaps the most perplexing signal of all is one that was never sent, a profound and telling silence from an object that seemed, by all other accounts, to be wide awake. Astronomers observed this visitor with a sense of eager anticipation. Here was a comet doing everything a comet should. Its nucleus was a bright, fuzzy ball, its tail a clear stream of dust catching the sunlight, a classic portrait of vigorous activity. Spectrometers confirmed it was venting gas, likely water vapor and carbon dioxide, into the void. Yet, when they tuned their most sensitive radio telescopes to the frequencies where such comets typically broadcast their presence, they were met with nothing but the empty hiss of the cosmos. It was radio silence of the most deafening kind. This wasn't an inactive, dormant rock. It was a bustling, outgassing body that had somehow lost its voice, a paradox that forced a complete re-evaluation of what we thought we knew about the most fundamental cometary processes. The silence itself became the signal, a clear and baffling message that something about this comet's very nature was fundamentally alien. To grasp the depth of this mystery, you need to understand why comets are usually so chatty on the radio dial. In a typical solar system comet, the process is a lively and well-understood symphony. As the comet nears the sun, its frozen gases turn to vapor, creating a vast, fluffy atmosphere called the coma. This gas is then ionized by the sun's intense ultraviolet light, meaning its atoms are stripped of their electrons, creating a cloud of charged particles. This ionized cloud, or plasma, is the key. It interacts directly with the solar wind, that relentless stream of charged particles flowing from the sun. This interaction is a turbulent, energetic dance. The solar wind's magnetic field gets draped around the coma, compressing and contorting, while newly born ions are picked up and accelerated to tremendous speeds. All this violent motion and magnetic reconnection acts as a powerful natural radio transmitter, generating a broad, crackling static that astronomers can easily detect. It's the sound of a comet actively engaging with its stellar environment, a predictable and reliable signal of life. The utter absence of this radio noise from our active interstellar visitor meant that this entire chain of events was broken. The comet was venting gas, but that gas was failing to become the energetic plasma needed to start the conversation. This radio silence points compellingly toward one of two extraordinary possibilities, each revealing a different facet of this object's alien heritage. The first centers on the unique chemistry of the gases themselves. What if the material boiling off this comet was simply incapable of becoming efficiently ionized? In our own solar system, the dominant gas is water vapor, which breaks down easily into hydrogen and hydroxyl ions, creating a perfect plasma feedstock. But if this interstellar comet was venting a much more stable, noble gas-like substance, the entire process could stall. Molecular nitrogen is a prime candidate. It's a notoriously inert gas, a pair of nitrogen atoms locked in a tight triple bond that requires immense energy to break. If this comet's volatiles were dominated by nitrogen ice, the sublimating gas would form a neutral cloud that is largely transparent to the solar wind. The particles would be there, but they would lack the electrical charge needed to interact with the sun's magnetic field. Imagine the difference between trying to push a pile of iron filings with a magnet versus trying to push a pile of wood chips. The magnet has a powerful effect on one and virtually none on the other. This comet's coma in this scenario was like a cloud of wood chips, allowing the solar wind to simply blow through it without the friction and turbulence that generates radio waves. Its activity was real, but its chemistry made it electromagnetically silent. The second possibility is even more fascinating, suggesting a surface so pristine it lacked the very catalyst for ionization. In our local comets, the initial ionization is often kick-started not just by sunlight, but by the presence of countless tiny dust grains. These minuscule particles, lifted from the surface by the escaping gas, provide vast surface areas where complex chemical reactions can occur, helping to strip electrons from atoms and kickstart the plasma formation. They are the kindling for the radio fire. Our interstellar visitor, however, might have possessed a surface devoid of this fine catalytic dust. Perhaps it was covered in a hard, crystalline crust of pure ice, or its dust grains were so large and heavy that they simply fell back to the surface, never becoming entrained in the outflowing gas. Without this dusty kindling, the process of turning neutral gas into a charged plasma could have been incredibly inefficient. The gas would flow out, a silent, transparent wind, but it would never transition into the bright, crackling plasma shell that announces a comet's presence to radio telescopes. This object was active, but its activity was happening in a vacuum, both literally and figuratively. Its internal processes failing to connect with the external forces of the star it was visiting. This radio silence, therefore, stands as one of the most elegant and frustrating signals in our entire collection. It doesn't shout with strange data, it whispers by its absence, forcing us to recognize that even the most familiar cosmic phenomena can operate by a completely different set of rules when they originate from a distant foreign shore. As our celestial detective story continues, we encounter one of the most haunting and persistent signals of all, a ghostly warmth that lingered in the void long after the comet itself had vanished from sight. Astronomers were conducting a routine survey of a seemingly empty patch of sky with a powerful millimeter-wave telescope, an instrument designed to see the faint heat glow from the coldest dust in the universe. They expected to chart the familiar, frigid background, but instead they found an anomaly. A faint, warm smear of emission hung in space, precisely tracing the trajectory where an interstellar comet had passed months earlier. This was no ordinary debris trail. The fine dust and gas from a typical comet are quickly blown away by the pressure of sunlight or dispersed by the solar wind, vanishing within days or weeks. This signal, however, persisted. It was a millimeter-wave afterglow, a remnant heat signature that refused to fade, suggesting the comet had left behind something far more substantial than the usual cometary fluff. It was as if a speedboat had passed through a still lake, and long after its wake had subsided, the water itself retained a mysterious, lingering warmth, a thermal memory of the object's journey. The longevity of this afterglow was the first major clue. For this heat radiation to remain detectable for so long, the material responsible had to be made of sterner stuff. The signal pointed directly to the presence of unusually large, warm dust grains. Think of it like the difference between throwing a handful of fine flour into the air versus tossing a handful of coarse sand. The flour will form a cloud that instantly disperses on the gentlest breeze, while the sand grains, being heavier, will fall to the ground in a more concentrated, lasting pattern. In the vacuum of space, the breeze is the radiation pressure from sunlight. Tiny, submicron dust particles are pushed away almost immediately, but larger grains, perhaps the size of sand or even small pebbles, have enough mass to resist this pressure. They continue to coast along the comet's original path, and because of their size, they also have more thermal mass. When warmed by the sun, they take much longer to cool down than their microscopic counterparts, allowing them to radiate a detectable heat signature in the millimeter band for months on end. The very existence of this persistent trail painted a vivid picture of the comet's composition, suggesting it was unusually rich in this coarse, gravel-like material, a veritable gravel pit spewing rocky debris into the interstellar void. But the composition of these grains was an even greater mystery than their size. The specific wavelengths of the millimeter wave glow hinted that we weren't just detecting simple silicate sand. The spectral signature contained subtle features that suggested the grains were not just warm rocks, but potentially complex organic molecules, perhaps even a form of interstellar soot or prebiotic material. In the cold, dark nurseries of planetary systems, simple ices on dust grains can be processed by stellar radiation into increasingly complex carbon-based compounds. These can include polycyclic aromatic hydrocarbons, essentially soot, or even more intricate molecules like the building blocks of sugars and amino acids. If this interstellar comet was a carrier of such complex organics, its journey through our inner solar system would have been a delivery mechanism on a cosmic scale. The heat from the sun could have baked these organics off the nucleus, sintering them into larger, warmer grains that then persisted in the afterglow. This transforms the image of the comet from a simple icy wanderer into a potential cargo ship for the raw materials of life, its departed form leaving behind a tenuous, warm cloud of astrobiologically significant material, a ghostly offering scattered along its path. The profound implication of this afterglow signal is what it tells us about the unseen legacy of these interstellar visitors. Every such comet that passes through our solar system may be seeding interplanetary space with a faint drizzle of large, warm, and potentially organic rich grains. While the dramatic, visible comets like Borisov capture our attention, it is this silent, lingering afterglow that may have the more lasting impact. This material, drifting through the solar system over millennia, could eventually be swept up by planets, their moons, or even asteroids, delivering exogenous organic compounds far from their point of origin. The trail we detected was a single, observable example of a process that has likely been occurring for billions of years, a continuous, gentle rain of complex chemistry from other star systems. The faint, warm whisper in the millimeter waves is therefore more than just a puzzle of physics. It is a tangible connection to the galactic cycles of matter, a hint that the ingredients for life itself are not just local products, but are being constantly traded across the vast distances between the stars, with every passing comet leaving behind its own unique thermal signature in the cosmic exchange. Continuing our deep dive into the data, we arrive at a signal that came not from telescopes pointed at the sky, but from instruments designed to catch the very substance of these cosmic visitors. As an interstellar comet made its journey through our solar system, it wasn't just observed from afar. A specially equipped probe was sent on a high-speed flyby, carrying an instrument called a dust impact mass spectrometer. This device is essentially a cosmic catcher's mitt, When tiny particles smaller than a grain of sand hit its target at incredible speeds, they vaporize into a cloud of ionized gas. The instrument then sorts these ions by their mass and charge, providing a real-time readout of the particle's chemical composition. The expectation was to see the classic signature of cometary dust, a mix of light elements like carbon, oxygen, and silicon, the building blocks of the silicate and carbon-based grains we find throughout our own solar system. But the data that streamed back was anything but classic. Each impact revealed a profile that was unexpectedly heavy with metal ions. The critical measurement, the charge-to-mass ratio of these particles, was consistently skewed, indicating that for their size, these specks of dust were carrying a surprisingly large amount of mass. It was as if you were tossing what looked like ping-pong balls, only to discover they had the density and weight of ball bearings. This anomalous ratio was a direct and startling signal that the fundamental recipe for dust in this alien system was radically different from our own. To understand why this is such a critical clue, think about what the charge-to-mass ratio actually tells us. When a dust particle vaporizes upon impact, the resulting ions have specific masses and carry specific electrical charges. A simple silicate grain, made mostly of magnesium, silicon, and oxygen, produces a characteristic, relatively light signature. But the data from this interstellar dust was dominated by heavier ions, things like iron, nickel, and even hints of more exotic refractory metals. These elements are much denser than the light, rocky material we're used to. A dust grain that incorporates a high proportion of these metals will have a much greater mass for its physical size compared to a fluffy silicate grain. This high density directly affects its charge-to-mass ratio, producing the distinct anomaly the instrument detected. It was clear we weren't looking at simple space dirt. We were analyzing microscopic nuggets of what seemed like metallic ore, a form of dust our solar system simply doesn't produce in such abundance. This discovery points overwhelmingly to a formation environment for this comet that was rich in metals, a place where the primordial soup of the protoplanetary disk had a very different blend of ingredients. In our own solar system's history, a process called thermal fractionation occurred as the disk cooled. Metals and other refractory elements, which can condense at very high temperatures, tended to do so close to the Sun, eventually forming the rocky inner planets like Earth and Mars. The outer regions where comets formed were dominated by lighter, more volatile ices and silicate dust. The profound abundance of metallic dust in this interstellar visitor shatters that model for its home system. It suggests that this comet must have formed much closer to its parent star, in a region that was so metal-rich that these heavy elements were incorporated directly into the cometary ices from the very beginning. Alternatively, it hints at a stellar environment that was fundamentally different in its chemical makeup. Perhaps the molecular cloud that collapsed to form this comet star was itself enriched by the cataclysmic explosion of a previous generation star, a supernova, that had seeded the area with an unusually high concentration of heavy elements. This comet, then, would be a literal piece of stellar shrapnel, its dust grains carrying the forged remains of a dead star within them. But there's another, equally compelling layer to this mystery. The data also suggested that many of these dense particles were not just metallic, but strongly magnetic. This implies the presence of ferromagnetic minerals like magnetite or metallic iron alloys that can hold a magnetic charge. The existence of such magnetic dust opens up a dramatic new possibility for this comet's early life. It suggests that its birthplace was not just metal-rich, but also permeated by an intensely powerful magnetic field. This is a hallmark of a young, volatile star in its T-Tauri phase, a type of star known for its fierce magnetic activity. If this comet formed within the reach of such a star's magnetic influence, that field could have acted as a cosmic sorting mechanism, selectively aligning and trapping these magnetic dust grains as the comet's nucleus was accreting. The magnetic field would have guided the very construction of the object, ensuring that these heavy, metallic particles were woven into its fabric from the start. This means the anomalous charge-to-mass ratio we measured is more than just a chemical signature. It is a fossilized relic of the powerful magnetic forces that shaped this comet in its cradle, a permanent record of the dynamic and energetic conditions around a star very different from our own placid sun. Just when we thought we had mapped the limits of these interstellar oddities, we witnessed a signal that tied their behavior directly to the violent, beating heart of our own solar system. This discovery didn't come from the comet's own internal clock, but from an external cosmic conductor, the Sun itself. Astronomers tracking one particularly active interstellar visitor noticed something that seemed to defy coincidence. On 3 separate occasions, as powerful solar flares erupted from the Sun and massive clouds of charged particles known as coronal mass ejections raced outward, the comet responded. But it didn't just respond, it erupted in perfect, unnerving synchrony. Within minutes of the solar storm's arrival, the comet's brightness would violently spike, and telescopes would capture massive jets of dust and gas exploding from its surface. It was a call and response across tens of millions of miles, a celestial dialogue where the Sun's shout was met with an immediate, explosive answer from the icy wanderer. While we know solar activity can influence comets, the sheer immediacy and ferocity of this reaction was unlike anything ever recorded from a resident of our own solar system. It was as if our local comets, when poked, would grumble and shift, while this interstellar visitor, when prodded by the same force, screamed and burst into flames. To appreciate the depth of this mystery, you need to understand the typical, more leisurely relationship between a comet and the Sun. In a normal solar system comet, the process of heating is a gradual affair. Sunlight, primarily in the form of visible light and infrared radiation, warms the surface over hours and days, slowly driving the sublimation of ices buried just beneath the crust. A solar flare or coronal mass ejection certainly supercharges this process, but its effects are usually buffered and delayed. The intense flash of X-rays and ultraviolet light from a flare hits almost instantly, but it only affects the very topmost layer of the surface. The bulk of the energy from a coronal mass ejection arrives later, in the form of a slower moving but incredibly energetic wave of plasma and magnetic fields. When this wave hits a typical comet, it energizes the gas and dust already in the coma, making it glow brighter, and it can increase the rate of sublimation. But the key word is increase. It amplifies an existing process. The near-instantaneous cannon-shot outburst from the interstellar comet suggested something far more direct and catastrophic was occurring. It pointed to a surface that wasn't just receptive to the Sun's energy, but was fundamentally and dangerously vulnerable to it. This hypersensitivity points toward a profound and compelling possibility that we are looking at a surface that has never developed a protective patina. In our own solar system, comets that make repeated journeys around the Sun undergo a kind of aging process. With each close pass, the most volatile, sensitive ices near the surface are burned away. What's left behind is a lag deposit, a layer of dust, complex organic goo, and tougher, less volatile materials that forms a dark, crusty insulating layer. Think of it like a cosmic version of the skin that forms on a cup of hot chocolate left out too long. This crust acts as a thermostat and a shield, regulating how deeply solar heat can penetrate and protecting the delicate ices hiding beneath. Our interstellar visitor, by stark contrast, appears to be a cosmic newborn in terms of its exposure to stellar fury. Having spent the vast majority of its existence in the deep freeze of interstellar space, it has never been subjected to the intense, repeated baking of a star. Its surface is likely pristine, a layer of ultra-volatile ices like carbon monoxide, molecular nitrogen, and perhaps even carbon dioxide, all sitting right at the surface, completely unprotected by any significant insulating crust. It is a comet in its most raw, primordial state. This lack of a protective layer creates a perfect storm for a violent reaction. When the initial blast of X-rays and extreme ultraviolet light from a solar flare strikes this pristine surface, it doesn't just warm it. It delivers a shocking, instantaneous energy dose that can shatter chemical bonds and trigger explosive sublimation in the topmost micron of ice. Then, moments later, the main wave of the coronal mass ejection arrives. This isn't just light, it's a physical onslaught. The cloud of billion-degree plasma and its embedded magnetic field slams into the comet's nucleus. For a surface without a crust, this is a direct body-level shock. The energetic particles can penetrate deep into the porous, open structure, dumping their energy not just on the surface, but within the very pores and tunnels of the nucleus itself. This internal heating causes trapped ices to vaporize explosively all at once, building up pressure that violently blows off any overlying material in the dramatic jets we observed. The entire object rings like a bell struck by a hammer, its entire structure responding instantly to the external shock. This synchronized outburst is therefore a signature of purity. It reveals an object that has been preserved in a state of deep cosmic freeze for perhaps billions of years. Its hyper-volatile skin, a direct, unedited sample of the conditions in the outer reaches of its home planetary system, now reacting with terrifying vigor to its first real encounter with a star's wrath. And now we conclude our journey with perhaps the most speculative, mind-bending signal of them all, a ghost in the machine that challenges our very perception of time and presence in the cosmos. Years after a known interstellar comet had faded from view, becoming a distant, unobservable speck on its way out of the solar system, a team of radio astronomers was sifting through archival data from a sensitive deep space monitoring network. Their goal was routine, to catalog background noise and pinpoint any anomalies. To their utter astonishment, they found one. A faint, repeating radio echo, a series of identical, whisper-quiet pulses, was recorded originating from the exact, empty region of space through which that comet had traveled months, even years earlier. The signal wasn't a natural cosmic burst. Its structure was too simple, too clean. It was an echo, but not the kind that bounces off a canyon wall. This was an echo with a delay of epic proportions, a signal that had been held in suspension, only to be released back into the void long after the object that supposedly caused it had departed. The most startling part, when researchers analyzed the echo's frequency and modulation, they found it was a near-perfect match for a powerful, human-made radar transmission that had been directed toward that sector of the sky years before the comet had even arrived. It was as if we had shouted into the cosmos, and the universe had waited for a passing messenger to catch our words and gently, belatedly, whisper them back to us. The leading hypothesis to explain this bizarre phenomenon is as beautiful as it is radical, suggesting the comet left behind a temporary, self-organizing mirror in its wake. This theory centers on the behavior of complex ices under the intense radiation of deep space. As the comet journeyed through our solar system, the sun's heat sublimated its volatile ices, releasing a vast cloud of water vapor and gas. But this wasn't the end of the story. In the frigid vacuum far from the sun, this ejected cloud of gas would have begun to refreeze. However, without a solid surface to crystallize upon, the molecules didn't just form a random fog of ice dust. Instead, they may have undergone a process of self-assembly, structuring themselves into a vast, tenuous cloud of highly uniform, hexagonal ice crystals. Think of it like a sudden, cosmic frost forming in the shape of a perfect, invisible honeycomb stretching for millions of kilometers along the comet's trajectory. This isn't just ordinary ice, it's a crystal lattice with incredibly precise geometric properties. For a specific frequency of radio wave precisely the frequency of that human-made radar pulse, this expansive, drifting cloud of crystals could have acted as a perfect, distributed Bragg reflector. Just as the specific spacing of atoms in a crystal diffracts X-rays, The specific size and spacing of these ice crystals could have been tuned to coherently reflect that one specific radio frequency, while allowing all other radiation to pass through unimpeded. The original human transmission shot past the comet, continued into deep space, and eventually struck this lingering crystalline ghost. The cloud then acted like a colossal cosmic diffraction grating, catching the signal and focusing a tiny, coherent fraction of it directly back toward its point of origin, Earth. The echo was faint because the cloud was diffuse, and it repeated as the cloud slowly rotated and drifted, its alignment briefly perfecting itself at intervals, allowing another faint pulse to be reflected our way. This incredible notion forces us to confront a new, dynamic vision of the solar system's environment. We often picture the paths of celestial objects as empty, pristine highways. But this echo signal suggests they can be littered with temporary, complex structures, intricate artifacts fashioned from a comet's own expelled breath. The implications stretch far beyond a single strange signal. If this process is real, then the solar system could be crisscrossed with these ethereal, crystalline architectures, the lingering contrails of every active comet that has ever passed through. Each one would be a unique, evolving structure, its reflective properties changing as it slowly disperses or gets reshaped by the solar wind. They would be invisible to our telescopes, yet capable of subtly manipulating the radio waves that pass through them, creating a hidden layer of cosmic optics that we are only just beginning to suspect. This transforms the interstellar comet from a simple messenger into a master sculptor, an artist that uses its own substance to create fleeting, invisible art in the void. The echo we detected would then be a single chance interaction with one of these grand, temporary installations, a momentary alignment that allowed us to hear our own voice, delayed by years, returning to us from a sculpture that has long since faded back into the formless dust of the galaxy. It's a fittingly profound end to our exploration, a signal that blurs the line between the natural and the artificial, and suggests that the universe is not only stranger than we imagine, but capable of a subtle, structural artistry we are only now learning to perceive. And so our journey through these 25 cosmic whispers draws to a close. We have traveled from the radio chatter of a singing comet to the ghostly warmth of a fading dust trail, from the violent flicker of a disintegrating rubble pile to the profound silence of a comet that refused to speak. Each signal, in its own unique language, has told us a piece of the same incredible story. These interstellar nomads are not uniform, they are a testament to the boundless creativity of the cosmos. Some are pristine time capsules, their surfaces never touched by a star's heat until they met our sun. Others are ancient shards of shattered worlds, their metallic hearts and complex debris fields hinting at violent pasts in distant solar systems. Some communicate through the elegant warping of spacetime itself, while others broadcast their presence through brilliant, anomalous chemistry written in light. This isn't a catalogue of oddities, it is a gallery of possibilities, each entry a direct sample from a different corner of the galaxy, proving that the recipe for building a planetary system is not a single, rigid formula, but a vast and varied cookbook. The true power of these 25 unexplained signals lies not in any single shocking revelation, but in the collective portrait they paint. Think of them as individual pixels in a grand cosmic image that is only now coming into focus. The strange shape of Oumuamua, the unique water of another, the heavy dust of a third, these are not isolated curiosities. They are interconnected data points in a new science of comparative planetology that stretches across light years. Every anomalous ratio of deuterium to hydrogen, every bizarre polarization signature, every unexpected burst of gamma radiation is a clue. It tells us about the temperature, the chemical abundance, the magnetic fury, and even the historical violence of the alien cradle where that object was born. By studying these visitors, we are no longer just guessing about exoplanets from the wobble of a distant star. We are holding pieces of them in our hands, metaphorically speaking, and analyzing their very substance. We are learning that our solar system, with its specific arrangement of planets and its particular blend of elements, is just one neighborhood in a galaxy of staggering diversity. As you look up at the night sky, let this knowledge settle in. The darkness between the stars is not empty. It is a bustling crossroads, a celestial highway constantly traversed by these silent, ancient travelers. For every one we have been fortunate enough to detect, countless more are slipping past unnoticed, dark comets, icy shards, and rocky fragments, each carrying its own untold story. The next great cosmic signal might be streaking through the outer solar system right now, a whisper on a radio band we haven't thought to check, a spectral line we haven't thought to look for, or a gravitational tremor we haven't yet felt. The universe is speaking to us through these messengers. We only need to learn how to listen more carefully. So the next time you find yourself beneath a clear, starry sky, take a moment. Wonder about what might be passing by, unseen and unheard, in that vast, silent expanse. What other secrets are these interstellar nomads carrying? What other wonders are waiting to be discovered? The conversation has only just begun, and your curiosity is a vital part of it. Share your own thoughts, your wildest theories, and your questions in the comments below. Let's keep looking up